Yeah. Yeah. Good morning, everyone. Uh, okay. So let me put it in the slideshow. So this is the problem where we have stopped the other day in the other class. Okay. So you are asked to find out Vx in the circuit shown. Okay. This is your circuit. If you just observe, this is your circuit. Okay. So if you just observe here, there is a dependent source. Okay, I think everyone is aware of the dependent sources. Now tell me, what is this dependent source? This is the fourth time I am asking the question. What is this
Current
dependent?
dependent voltage source.
Very good, very good. Current dependent voltage source. Okay, first of all, you need to observe what are the sign conventions within this diamond shape, source. So whenever you have a diamond shaped source, that is called a dependent source. Generally, dependent sources are mentioned or drawn in the form of this shape, whereas independent sources will be drawn in this shape in the form of a circle. Okay, so dependent sources will be drawn like this, and you need to observe what is the sign convention here. So sign convention is plus and minus. Plus and minus, wherever you observe, that will be a voltage source. Okay, if you have a arrow mark, that will be a current source. First of all, it is a voltage source. On which parameter it is depending, that will be shown here. Okay, which parameter it is depending? If it is given as V, then it will be voltage dependent voltage source. Since it is given as I here, okay, so this is a voltage source first, which is depending on some other current. That current I is the current which is flowing through this 1 ohm resistor. Okay, so this will be a current dependent voltage source. That is the point. So you can proceed even though you have a dependent source or any independent source or whatever it may be. First of all, you need to observe whether you have any voltage source in between, okay, the meshes. If you have a voltage source in between the meshes and you are asked to solve the problem using mesh analysis, then there is no problem if you have a voltage source. But if you have a current source in between two meshes, then you will have a problem that you cannot apply KVL to the meshes. So whenever you have a current source and you are asked to solve the problem using mesh analysis, then you need to observe that you are not able to apply KVL to any mesh. Okay, so that forms a super mesh. Okay, that already we have discussed in the previous problem. I have already given you the assignment. Hope everyone is working on the assignments. Okay, if you don't understand, uh, I already shared the material in the Google Classroom. You can check out the material. You just study it. And then if you want me to share the recordings, I'll be also share the recordings of our classes. Okay, don't worry. I'll just work out on whether I can upload the recording or not. So if it is uploaded, I'll be uploading in the Google Class. You can also view my classes, whichever are completed. Okay. So you just observe here. I can apply KVL to this mesh. I can apply KVL to this mesh. I can also apply KVL to this mesh. So you can go with applying KVL to all the meshes. Okay, you have a voltage source here. I don't have any super mesh in my problem, so I can solve this. The problem here is, what is the value of I that you need to observe? So what will be the value of I here? I is the current which is flowing through this 1 ohm resistor. So which is nothing but the branch current through this 1 ohm resistor. Okay. So how the direction of I is? The direction of I current is in downward direction. So which current is in the same direction as that of the direction of I here, I1. So the current which is flowing through 1 ohm resistor will be I1, since it is flowing like this, minus I2. Why? Because this I2 is coming in the reverse direction. You just observe. I'll just go to my Jamboard. Okay. Hold on. Hold on, please. I'll just share my Jamboard. I don't find this. Why I am unable to find? Hold on, please. Yeah. Hold on once. I'm unable to find my Jamboard. What are you able to see in my screen? What is it I am, what is that visible to you once? Tell me. Nothing is visible, right? So I don't understand why I'm unable to share my Jamboard. Okay. Hold on once. Okay, fine. Let us go with this. I don't know why I'm unable to share. Till yesterday it is fine. Okay, fine. You just observe here. This is our KVL. I mean, I can apply KVL to this loop. I can apply KVL to this loop. Okay. Hold on. Hold on. Yes, please. Yeah. Sorry for the delay. Okay. You just observe here. Yeah. For mesh 1, if you observe, okay, so this is plus and this is minus. This is plus and this is minus. I can't write. You just take down the problem once, everyone. Take down the problem once. Make it fast. Just apply the sign conventions to each and every loop. So if you just observe, I can place plus, minus, okay, plus, minus here. Okay, if I apply KVL to this mesh, okay, so go like this, minus 8 plus 1 into I1 plus 2 into I1 minus I3. Why? Because this 2 ohms resistor is in between two meshes. Okay, plus 2 into I1 minus I3. Next, plus 1 into I1 minus I2. Why? Because this 1 ohm resistor is in between two meshes. Okay, is equal to 0. This is our equation. Next, coming to second mesh, if you just observe this mesh, so what will be the sign conventions for this 6 ohms resistor? Plus, minus, plus, minus, plus, minus, like this. Okay, so if you just start from here, okay, and go like this, in this manner, okay, so I can write minus 2i. If minus 2i is present or not, you just observe in the second equation, minus 2i is there. Next, if I go like this, plus 6 into I2 minus I3. Next, plus, minus, plus 1 into I2. Next, for this one, plus 1 into I2 minus I1 is equal to 0. This is our second equation. Hope you have taken down the circuit and you just apply KVL to each and every mesh. Next, coming to third mesh, okay, start from here, plus 4 into, what is the current flowing through 4 ohm resistor? I3. Next, coming to this, since this current I3 is flowing in this manner, plus 6 into I3 minus I2 because 6 ohms resistor is in between third mesh and second mesh. If you go on like this, plus 2I, why? Because I am entering in this direction. Because I3 current is flowing in this way. So when it comes here, plus 2I. So in this equation, if you have plus 2I or not, you just observe plus 2I. Next, go like this, plus minus. So plus 2 into this 2 ohms resistor is in between two meshes. So I3 minus I1. 2 into I3 minus I1 is equal to 0. Okay, you just solve these three equations, every one of you, and tell me. And okay, wherever you have I already told you I is nothing but I1 minus I2. So wherever you have I, you have to substitute I1 minus I2. So you will be getting three auxiliary equations. After getting three auxiliary equations, you just solve and tell me whether you got the same answers or not, every one of you. Okay, meanwhile, I'll check out what's happening with my Jamboard. Wait a minute. Are you solving, ma? Hello. Yes, please. Anyone respond? Are you solving?
Yes, ma'am.
Yeah, please solve and tell me what are the equations you got. Meanwhile, I'll check out where is my Jamboard. Every one of you have to solve, or else you will not understand. So don't just keep quiet. I want every one of you to solve the problem. Okay, is my screen visible now for everyone? You just observe once and tell me. Is it visible?
Yes,
Yeah.
ma'am.
Okay, fine. You just observe those who didn't understand. You just observe here. See, I have how I have took the sign conventions according to my mesh currents. Okay, so I have started here. If I have started here, okay, so go like this, -8. Okay, so since this current I1 is flowing in this direction, so it enters into 1 ohm resistor. Whenever it enters, you have to take it as positive. Whenever it leaves, you have to take it as negative. So I1 is entering into 1 ohm resistor in this direction, entering into 2 ohms resistor in this direction, entering into this 1 ohm resistor in this direction, in this mesh, only in that mesh, and leaving like this. Like this, this I1 is circulating in this loop in this manner. Okay, so those who have who are new, you just follow. Next, coming to I2, I2 has entered. Wait a minute. Here I have to give the sign conventions. This is plus and this is minus. Okay, so I2, it has entered the 6 ohms resistor in this loop. I am talking only in this loop. I am not talking about the sign conventions which are not in that loop. I am talking about I2 in this loop. Okay, so if you just observe, this is plus because it is entering 6 ohms. This is plus because this is entering 1 ohm resistor, and it is going like this. It is entering 1 ohm resistor here. This is plus and this is minus. Okay, this is how I2 is circulated in second loop. Now coming to third loop, when I start here, I3, it has entered 4 ohms resistor, entered 6 ohms resistor in this direction for this loop. So I have given plus for 6 ohms in this loop as plus here and minus here. Now go like this. Okay, this is plus here and minus here. Okay, so this is how I have given the sign conventions. So after giving sign conventions, you start from here, minus 8 plus 1 into what is the current flowing through 1 ohm resistor? Only 1 ohm resistor is individually in the first loop. It is not in between any two loops, isn't it? So what is the current flowing through 1 ohm resistor here? Only I1. So minus 8, okay, minus 8 plus I1, so 1 into I1. Next go like this, plus 2. 2 is observed to be in between two loops, isn't it? First loop and third loop. So plus, so whenever I am writing equation for that first mesh, I need to take the sign conventions within that loop, So I have been telling you continuously that you need to remember this. Okay. So within this loop only you need to consider the sign convention. So plus 2 into I1 minus I3. That is what it is written here. Okay. Next come like this, plus 1 into I1 minus I2. Okay. So that is how it is written like this, in this for this circuit, for this mesh. Now coming to second mesh, there is a dependent source, that to voltage source. Whenever you have a voltage source in between two meshes, there is no problem in writing KVL equation, because you are writing Kirchhoff's voltage law equation. So you can write Kirchhoff's voltage law equation even though you have a voltage source, because it is itself is a voltage. So you can write the equation. But whenever you have a current source, current you can't equate it to voltage equation. So some students are doing a mistake, that whenever you have a current source, you are just writing that 2 amps or 3 amps, okay, in the KVL equation. It itself is saying that it is a Kirchhoff's voltage law equation. It is not a current equation. You cannot equate voltage to current anywhere. Voltage is equated to voltage only. Okay, so that that depends upon the sign convention. So if you have pluses this side, if you take minuses that side, then both will be equal, like that. We cannot equate current to voltage. So this is how we'll be writing KVL equation for the first mesh. Now coming to the second mesh, when I start at this node, at this point, and go like this, minus 2i first, minus 2i. Okay, next plus 6 into I2 minus I3. Next plus 1 into I2 plus 1 into I2 minus I1. Okay, I2 minus I1 is equal to 0. Next, coming to third mesh, you start here, plus 4 into, what is the current flowing? I3. Now go like this, enter, plus 6 into, 6 is in between two meshes, plus 6 into I3 minus I2. Go like this. So you are entering into positive here. So plus 2i, go like this, plus 2 into I3 minus I1. Whenever you are writing equation for any mesh, that mesh current is assumed to be the highest current. So this current, if you take it as positive, highest, positive is always taken as highest. And since this I1 is coming in reverse direction to 2 ohms here, I3 minus I1 is taken like this. Okay. So this is how we have written the KVL equations. And this I, if you just observe, I, so I is in the same direction as this, as that of I1. Okay. So this I1 is flowing in this direction and I2 is flowing in the reverse direction. So I is equated to I1 minus I2, or else if you are confused, okay, you just apply KCL at this node, KCL at this node. Okay. So if you apply KCL at this node, so this I2 is coming in this direction because it is flowing and then coming like this, I2. Now coming to I1, I1 is coming like this and then leaving the node. So two currents are entering the node. Okay. What are the two currents? I plus I2, and one current is leaving. I plus I2 is equated to I1. I plus I2 is equated to I1. Right? So I will be automatically equal to I1 minus I2. That is how you need to check how to write down depending upon the direction of the currents. Okay. So after writing the KVL equations, have you solved it, everyone?
Yes, ma'am.
Okay, I have just to put this equation, first equation, I have solved it like this. Okay, so I got this equation. So if you just observe, this is 4I1 minus I2 minus 2I3 is equal to 8. Have you got the same?
Yes, ma'am.
Okay, now coming to, yeah, okay. Now coming to the second equation. Okay, so I2 minus I1, I have written here, minus 2 into, in place of I have substituted I1 minus I2. Next, plus 6I2 minus 6I3 plus I2 is equal to 0. If I just solve this, I got this equation. Have you got the same?
Yes, ma'am.
Minus 3I1 plus 10I2 minus 6I2 is equal to 0. Similarly, coming to the third mesh, okay, so 2I3 minus 2I1 plus 4I3 plus 6I3, okay, minus 6I2 plus 2 into, in place of I have substituted I1 minus I2. Finally, I got this equation. Have you got the same?
Yes, ma'am.
Okay,
Yes, ma'am.
fine. Finally, if you solve these three equations, this equation, okay, this equation and this equation, if you solve the three equations, you will be getting the overall currents. That means loop currents to be I1, I2, I3 to be these, isn't it? Have you got the same? Have you got the same, ma?
Yes, ma'am.
If you did not get the same answers, you would have done a mistake in either plus or minus. You have to be very careful in writing the equations. If you, instead of plus, if you write minus, then answers will go off. Okay, so you have to be very careful in writing the equations. Now, what is the question you are asked? You are asked to find out what is the value of Vx. Okay, so if you just observe Vx sign convention which is given, okay, Vx is sign conventions are plus and minus here, if you just observe. Okay, so so according to our yes, we just observe the sign conventions of Vx is plus and minus, whereas I have also given the sign convention for 1 ohm as plus and minus according to the direction of current which is flowing through 1 ohm, isn't it? So that means if you both are same potential, that means whatever the sign conventions according to the I2 current I gave are same as that of Vx sign conventions. So if you just find out the multiplication of I2 into 1, then you will be getting equated to Vx. Or else if you are confused, you just observe here. I have just drawn this 1 ohm here. If you just apply KVL to this complete KVL, you just apply, you start from this point. If you just start, so minus Vx, go like this, okay, plus 1 into I2, that means I2, minus Vx plus I2 is equal to I2 into 1. I2 into 1 is I2, isn't it? So you have multiplied it with 1 ohm resistor, then only you got I2. I2 value is how much? 2.82. Sorry, 1.41. So minus, I have started here, minus Vx, go like this, okay, plus 1.41 is equal to 0. So minus Vx, if plus 1.41 is taken to the right hand side, okay, so minus Vx is equal to minus 1.41. So Vx is equal to 1.41. So what is the meaning here is, whenever you have like this, plus here and minus here, so they are nothing but parallel, isn't it? Both are in parallel. So if you have parallel, both voltages will be equal. So Vx is equated to 1.41 volts because it is multiplied by 1 and 1.41 volts. So for example, if you have like this, if you are asked like this, According to my current direction, I have, according to my current direction, I have plus 1.41 into 1 ohm. Okay. So if you just apply KVL to this, okay. So here this is plus and here it is minus. Okay. Here you have minus and here you have plus. Then in that case, okay, the value of Vx will be just negative. So, or else you can check it by applying KVL. You just start from this point. Okay. So, what is, wait a minute, wait. I'll just put it in this way. I'll just put it in this way. Okay. So I2 is flowing like this. Okay. So this is plus and this is minus. And Vx is asked like this, minus Vx. Same you're getting. I will be starting. Okay. So I'll be starting at this node. You go like this. Okay. So plus at this point, if I start, plus 1 into I2, go like this. Okay. Plus Vx is equal to 0. Plus 1 into I2 plus Vx is equal to 0. So if you take Vx that side, it will be minus Vx. So both will be reversed. That's it. Okay. So if you have the sign conventions same, then the voltage will be equal at that. So Vx is equal to, that means you will be getting a positive value here. That is my point which I want to deliver. Okay. If the sign conventions are same here, then you will be getting a positive value of Vx. Vx is equal to 1.41 volts. If you have reverse sign conventions, then you will get a negative value. That's it. Am I clear up to here? If you have any doubt, you can ask me with this problem. Yes, ma?
And second case की equation
What, ma?
second case की equation आ रहा है opposite thing.
Second case equation you want. Wait, hold on. Second case. Okay. I'll just erase my. Okay. So you just see here. Okay. This is plus and this is minus. Okay. And this is my current I2. Right? So this is minus. This is plus Vx. You start at this point. At this point, you just start. At this point, if you just start, so what is your value? Plus Vx. Because you are starting here, you are in here. Plus Vx. Okay, you can't write plus Vx and minus Vx because already I have entered into this Vx. So plus Vx, go like this. So where is the starting point of this? This one. Plus I2. Okay, isn't it? Yes, no? Yes or no? Plus I2 into 1 is equal to 0. So plus Vx plus I2 into 1 is equal to 0. So if you take that I2 into 1 that side, you will be getting minus. So Vx is equal to negative value. Am I clear now? Am I clear?
Ma'am, if,
Yeah.
yes, ma'am.
Tell me.
If they ask the Vx in between the two meshes, then how to calculate it?
Yeah. It's a very good doubt. So if you are asked to find out Vx at this particular node, at this particular branch, isn't it? So Vx will be asked like this. So for example, if you are not given any sign convention for Vx, then you can take the value of Vx to be 1 into I1 minus I2. if you are not given any sign convention. For example, if you are given sign convention for Vx like this, Vx, okay, here you are asked now. So what will be your value? So which terminals are same as that of this Vx? If you just observe, which terminals are same? This side terminals. Yes, that means this side terminals, isn't it? So this 1 ohm, what is the current flowing through this 1 ohm resistor? I, isn't it? I. What is I? I1 minus I2. So 1 into I1 minus I2 will be your Vx value. Am I clear? Okay. Am I clear? Shall I go to next one?
Yes, ma'am.
Every one of you. Am I clear?
Yes, ma'am.
Okay, if you just practice dependent, I'll be posting the assignment also today for dependent problems also. Okay, there is no such, no such material also for dependent sources. So whatever class you follow, I'll just post some 2 to 3 problems. You just practice them, try to get the solutions, then you will understand. Okay, fine. Next, coming to our next topic, I'll just go to my PPT once. Yeah. So we have seen the problems I am done with the mesh analysis. Okay. So we have seen problems related to mesh analysis, super mesh analysis. Okay. Next, dependent sources problems in super mesh as well as in mesh, everything is done. Okay. So if you come across, if you practice more and more problems in dependent sources and independent sources, super mesh, mesh, then you will be perfect for this method. Now coming to our next topic, which is called nodal analysis, or nodes analysis, we can call it as. So nodal analysis is nothing but if you apply KCL to any node. Okay, node, when I talk about here in nodal method, when I talk about node here in the sense is a junction, essential node. So I told you what is the difference between an actual node, a junction, okay, or essential node. A junction can also be known as an essential node. So what's the difference between a junction and a node? Node is the meeting point of 2 or more branches, whereas a junction is meeting point of 3 or more branches. Okay. So here, coming to our KCL, so what do you mean by KCL? KCL is the algebraic sum of the currents entering and leaving the junction is equal to 0. Okay, the algebraic sum of the currents entering and leaving the junction is equal to 0. That is our KCL. We are going to apply first KCL in our nodal analysis method along with Ohm's law. So nodal analysis is the combination of Ohm's law and KCL, whereas mesh analysis is the combination of KVL and Ohm's law. In mesh, if you come across a current source in between two meshes, then it forms a super mesh, and super mesh analysis is the application of KVL, KCL along with Ohm's law. Here also you will be coming across a super node method that I will tell you where and when you come across that type of situation. So once you are aware of how to apply KCL at the nodes and how to solve the problems, then you will be able to understand the super node analysis method. Okay, so in KVL method or in mesh analysis method, what is the solution you first derive? You have derived the loop currents, isn't it? What you have derived? You have derived the loop currents. Once you get the loop currents, then you are able to find out branch currents. You are able to find out the voltages across the branches. you are also able to find out the power delivered to all the branches once you know the branch currents and voltages. Okay, but in case of nodal analysis or node method, you are going to find out the node voltages first. Okay, so here, if you want to understand about nodal method, first of all you need to understand what is a junction. A junction is any point in a circuit where, okay, two or more circuit parts come together. Two or more circuit parts come together. Okay, circuit parts is different. So if you just observe here, you see here in this particular one, there is a common node here, isn't it? So this is a node, this is a node, this is a node, this is a node, which is common to all the okay points here. Okay, next coming to this one, here another common node here. Okay, so coming to this, this can be redrawn. This can be redrawn as a one node which is connected to all the others. So all are parallel here. Okay, this is called a junction. Okay, this is called a junction here. So this is a circuit element, this is a circuit element, this is a circuit element. Okay, all form the circuit paths, right? Next, so that is what the equation for KCL, some algebraic sum of the currents entering and leaving the junction or a point, okay, in a circuit must be 0. Sum of the currents entering is equal to sum of the currents leaving, okay, the junction, then it also called as KCL. That is what is here. We just observe, okay, so the currents which are entering, how many currents are entering? I2, I3, I1. So what are the currents leaving? I5, I4. Okay, so if you mention the entering currents to be positive and leaving currents to be negative, then I1 plus I2 plus I3 minus I5 minus I4 is equal to 0. This is the meaning of algebraic sum. Okay, so algebraic, when I talk about algebraic sum, that is a combination of positives as well as negatives. Okay, when I talk only sum, then I1 plus I2 plus I3 will be equated to I4 plus I5. That is only the summation, then that is called the sum. Algebraic sum means we are adding negatives as well as the positives. Okay, so sum of the currents entering is equal to sum of the currents leaving, okay, at a junction point, then it is also termed as KCL. Okay, so analysis of nodal analysis is analysis using KCL to solve for voltages at each node of the network. That means at each, you need to first of all identify what are the nodes, essential nodes in the circuit. Then you are going to apply KCL at each and every node of the network and hence determine the currents through the branches and voltages across each element of the network. Okay, that is called nodal analysis. Application of KCL at each and every node. Okay, finding out the node voltages. After finding out node voltages, finding out the currents which are flowing through the branches is nothing but nodal analysis. Okay. So what is the procedure you need to follow for nodal analysis here? First, what you need to do, determine the number of common nodes and reference node within the network. I'll tell you what are the common nodes and reference nodes. Assign currents, okay, assign currents and its directions to each distinct branch of the nodes in the network. You need to assign currents. Apply KCL at each of the common nodes in the network. Solve the equations. Determine the node voltages and branch currents. So first what you need to do? First you need to identify what are the common nodes and reference nodes. Second, you need to assign currents at the common nodes. After assigning the currents, you need to apply KCL at each and every node. After applying KCL at each and every node, okay, you need to write down the simultaneous equations. Okay, KCL, these are all KCL equations, mind you that nodal analysis, okay, all are KCL equations, current equations. Okay, So from the current equation, you are going to find out the node voltages. How? I'll tell you. Right. Next, determine the currents through and voltages across each and every element. This is how we'll be applying nodal method. Now I have a circuit like this. Okay. So in this circuit, you need to identify what are the common nodes and reference nodes. Right? If you just observe this circuit, this is one branch, this is another branch, this is another branch, another branch, another branch. Okay, so these are all branches, no doubt. But in nodal analysis, you need to consider this is one node, ma. This is one node because this is a combination of two branches. This is one node. This is another node. Okay, and this is all one common node because this negative, this 40 and this minus 20 all are connected to a single point. Okay, so here you have a node, here you have a node, but in this method we are not going to apply KCL at this node and at this node. Why? Because the current flowing through these two is same, isn't it? Because both are in series. Okay, so from here the current is leaving and here it is entering. So these two branches, okay, both are considered to be the essential branch. Common. In common, these two mainly are called as essential branch. Okay, so from here to here, from here to here, this complete path is considered to be an essential branch. Now coming to this point, this one, this is a connection of three or more branches. So this is considered to be an essential node. So nodal analysis is applied to essential nodes but not normal nodes. Okay, so this is an essential node also called as a junction. So mind you that nodal method is applied to junctions. So generally we can't call it as a junction analysis, we call it as a nodal analysis because we are applying KCL to essential nodes. So now we just observe from here to here, okay, only one branch is connected. Next, coming to this one, again the current flowing through these two are same. So this both are considered to be essential branch. Now totally how many essential branches we have? Tell me. Yes, please. Anyone respond? Total how many essential branches we have?
5.
Yes. Essential I told. How many essential branches we have? 3. Very good. 3. That's what I told. See, normally we have 5 branches, but I am talking about an essential branch. So both are considered to be one branch here because the current flowing through these two is same. So 1, 2, 3. So 3 essential branches are there in this circuit. Okay. So how many essential nodes are there? Essential node is one where you connect 3 or more branches. So this is one essential node, isn't it? This is another essential node because 1, 2, 3 are connected. So this is 1, 2, 3 are connected. So this is one essential node, this is another essential node. So how many essential nodes here? 2, 3 essential branches. So number of node equations, okay, which can be possible for a circuit is equal to number of essential branches minus 1. You make a note. N minus 1, where n is number of essential nodes. So how many nodes are there? Essential nodes 2. 2 minus 1. Only one node equation is possible here. That is my point. Okay, so let me share my Jamboard once and then we'll go to, okay. Are you following? I'll show you once, don't worry. I'll show you. Yes. So if you just observe this circuit once, okay, this is the circuit which I have taken from my PPT. You just observe here. Okay, are you able to see my screen?
Yes, ma'am.
Yes, ma'am.
Okay, okay, wait a minute. I think I have not. Okay, fine. I'll show it in my this one only because I didn't make it out in my Jamboard. Okay, I'll just share my PPT once again. Okay, so if you just observe here, this is the circuit, isn't it? So if you just see this circuit, I told you that this is my junction point. So this is called, okay, a common node. What is this called? A common node. And this is called or else this can be called as a non-reference node. What is this called? This node is called a non-reference node. Then what about this node? This node is called reference node. Why this is called reference node? If you just observe this is a negative. This is also a yes, please. Okay, this is a negative. This is negative, and this is another 40 ohms resistor another end. So this connection, this connection, this connection, this is called a reference node. Why this is called a reference node? I'll tell you. Because there is no another connection along with this one or along with this one or along with this one. There is no other any other resistor or here or any other resistor here or any other element which is connected to these sources or this resistance. So all are joined. I think in your first year BW lab you would have seen the ground connections, isn't it? You will be grounding all the negatives, all the other ends of the resistors to the ground. So that is called a reference. So this can be called as a reference. So how can you identify a reference node? For a reference node, okay, that is an endpoint. No such, along with this negative, no other element is connected. For example, if there is a resistor here, okay, this cannot be called as a reference node. For example, if there is a resistor here, this cannot be called as a reference node. Okay, so if nothing is connected here, nothing is connected here, and nothing is connected here, then this can be called as a reference node. Okay, then what about this node? This is called a non-reference node. Okay, so this is called a non-reference node. So you need to apply KCL to a non-reference node. Okay, so in mesh analysis, we have assumed the direction of currents, isn't it? Either clockwise or anti-clockwise, you have assumed. Here also, at a non-reference node, okay, you need to assume that this node, the voltage at this particular node with respect to the reference is very, very high than any other voltage in the circuit. Either it may be 100 volts or 1000 volts or 10,000 volts here or here, whatever it may be. Whenever you are applying KCL at a non-reference node, you just assume that this node voltage is the highest voltage. Okay, so whenever this voltage is assumed to be the highest voltage, the current always flows from the highest potential to the lowest potential, highest potential to the lowest potential, highest potential to the lowest potential. So that is why I I have assumed this to be the highest voltage. So the direction of currents are leaving the branch, leaving the node, like this. Am I clear? Do you have any doubt? So whatever the sign convention here for this voltage source or for this voltage source, you just, okay, forget about whether current is coming from this direction or this direction, whatever the direction, you just forget about. Whenever you are applying KCL at a non-reference node, you assume that this voltage with respect to the reference is the highest voltage than any other voltage in the circuit. So the current starts from a highest potential to the lowest potential. So like this, like this, like this. So all are leaving. So can I apply KCL? The sum of this current, and this current is equal to 0. Then what about how to write down KCL for this particular direction of current? The current is flowing in this manner. So whenever I am applying KCL, okay, so these are the steps, right? So how the solution is, you just observe. Apply KCL at node A. Okay, so node A, this is the equation. How we wrote this equation? You just observe here. How I wrote this equation? So when I am going in this direction, you need to observe. I'll go like this and end up here, isn't it? So I'll go like this, end up here. Go like this, end up here. So whenever I am going like this, so VA, so this is the voltage with respect to the reference. VA is the voltage with respect to the reference. So what is the meaning here? The value of VA here it is positive and here it is negative. We can say that VA is the voltage across this 40 ohms resistor, okay, where this is negative and this is positive. Okay, so VA, so when I am going in this direction, you need to take okay, so VA minus 10, so minus 10, that means the last which is connected to the reference you need to check out. So do you have a positive sign or a negative sign? If you have a negative sign, VA minus 10. If you have a positive sign here, VA plus 10. Okay, so VA minus 10 is the voltage. Then we are not writing the voltage equation here, we are writing the current equation. So VA minus 10 divided by the resistance is the current value, isn't it? V divided by R is I value. We are writing KCL equation, mind you. V divided by R. So that is why I wrote VA minus 10 divided by what is the resistor which is connected to, okay, connected to these two voltage sources. VA divided by, so VA minus 10 divided by 10. Okay, this is the first current which is leaving. Plus, now coming to this one. Is there any voltage source here? There is no voltage source. Okay, so what is the potential at this point C? The potential at this point C will be 0. Okay, so VA reference always the potential is 0. Okay, so VA minus 0 divided by 40. Voltage divided by resistance is the current. So VA minus 10 divided by 10 plus VA divided by 40 plus again this current. See, I am writing a KCL equation here. All the currents are leaving. Okay, sum of the currents, algebraic sum. All are leaving, all are positive. We took it as positive. Or you can take them as negative. Anyhow, it is equated to 0 and then you will be getting a positive value only. Okay, next. VA, this along with this resistor, a voltage source is connected. So if you have a current source, that case is different. I'll tell you that also. Okay, so VA, what is the connection which is connected to the reference? Negative. So VA minus 20 divided by 20. VA minus 20 divided by 20, okay, is equal to 0. So this is how we'll be writing the KCL equation. Okay, so you just observe. I'll just wind it off it in 1 minute. No, don't worry. So this is our equation. See how I wrote? VA minus 10 by 10 plus VA by 40 plus VA minus 20 by 20 is equal to 0. Okay, so if I simplify this, this is the first equation. If I simplify this, I wrote again. Okay, we have to take the LCM for this 10, 40 and 20. So LCM is 40. Okay, so you take the LCM here. I mean 40 goes in 10 4 times. So 4 VA. Okay, next I wrote this minus 40 here. Next 40 goes in 41 time. So 1 VA. Next 40 goes in 22 times. 2 VA minus 40 is equal to 0. Okay, so if I simplify this, 4 plus 1, 5 plus 2, 7 VA minus 80 divided by 40 is equal to 0. So if I just simplify this again, 7 VA is equal to 80. Okay, so I got VA 80 by 7, which is equal to 11.42 volts. So that means I got the voltage at the node A, okay, at the node A with respect to the reference. See, voltage will not exist only at a point. Okay, that means you don't go in this way. The voltage at this node, okay, is the voltage at this node is only at this point is 11.42. No, the voltage at this point with respect to the reference, okay, is 11.42 volts. That is the point. Okay, so that is how we wrote the equation. So once you get the node voltages, you can now find out what is the current flowing through 10 ohms, which is VA minus 10 divided by 10. VA, once you get VA value, you can find out the current here. VA divided by 40 will be the current flowing here. VA minus 20 divided by 20 is the current flowing in this branch, in these directions only, in these directions, away, towards this. Okay, so I'll just stop this. We'll just continue in the next class. Meanwhile, I'll give assignment in the mesh problems. Okay, please type your roll numbers in the chat box and just leave so that your next class will be starting. Okay. Please type your roll numbers so that the next class will be starting in the chat box.